So now we're into round 3 already. This is, again, the third round that a POV could be successful, round 1 being the very first round that they could have as the challenges were deployed in round 0. And let's see how many we've got.
Yeah, we see a lot of scoring here by Xandra on this challenge. They seem to have got to everyone on that one there.
And that's one of the gold ones, right? Tell me more about those.
So the gold hex tiles represent challenges that we call the rematch challenges.
And you were the author of the rematch challenges too, so I think you know a little bit about them.
I know a little bit about them. I wrote this set of challenges, and what we were trying to do here is create challenges that reflect some well-known real-world bugs. This is not only so that we can kind of understand what this technology is capable of, but to make it accessible to the audience too. So these challenges they're all custom code, just like any other challenge in the game, but the vulnerability is very closely patterned after the vulnerability that was exploited in the real world.
I mean, I remember some of these. SQL Slammer, for example, got me in on call of the weekend to come into the university. I worked at the time
Saturday,
to fix.
yeah,
I remember that one. There was definitely some serious impact from some of these, or others very interesting technical details about them that kind of makes them fun, I think.
Absolutely. So the one that we just saw being exploited was the address resolution service.
That was my Saturday.
That was your Saturday. So this one's patterned after the SQL Slammer bug. You may have known at the time. If not, this was a very straightforward stack-based buffer overflow. It wasn't actually a SQL injection, as some people might think, maybe the younger crowd.
Based on the name, yeah.
But it was a companion service that ran next to Microsoft SQL Server, and all it was doing was trying to provide resolution for multiple instances running on the same server.
So when you've modeled it, you've recreated this similar kind of vulnerability. You've done it in a different service and different protocol, because all of these protocols are unique, but just inspired by, maybe? Is that a fair way to say it?
Yeah, absolutely. It's not using the original protocol, but it's using a new protocol that is suspiciously similar to the original.
And the reason for that, too, is that so that none of the competitors came in with foreknowledge. So if you tested your system on existing vulnerabilities,
which we presume that they would.
They most likely would have done. It gave them a leg up in terms of developing techniques and approaches, but it doesn't actually mean they sort of have a hard-coded recognizer for that protocol.
So special characters are changed.
Right. There's no HTTP, there's no SMTP, there's no standard protocol that we'd be familiar with as it is. It's going to be different for the game.
Yeah, exactly. So we can look at the code right here. We see the vulnerability. Up at the top, we have a stack buffer being declared of 64 bytes long, and then we have a very suspicious string copy that isn't bounded by length. So we're copying arbitrarily off of the network into that stack buffer. That's your buffer overflow 101.
It happens a lot for sure, and the stir copy to stir in copy is common. And I noticed it's inside of this if-def, right? So all of the authors had to define an official patch, I guess we could call it, right?
Yeah, so we wanted to make sure that the vulnerability was patchable, right, obviously, as part of the game, and then it was part of the automated infrastructure. Just putting this code in here allowed us to build a patched version, an unpatched version, and then do some testing against it. You can see here, obviously, that if we had written secure code, we would have used the string copy with a length bound on it to 64, so we make sure that we don't overflow that buffer.
To match that, length of the stack.
This is a really interesting view. So this is the first time we're seeing this here. This is called the filament view. This is something that was designed by DARPA specifically for this challenge to try to make the concept of a computer running a program something that the average person or even a technical person could see and understand a little bit better. So you are heavily involved in this. Why don't you describe what we're looking at?
I love the filament view. The filament view is a Hilbert curve. If you look at this plane, everything in this plane, as it kind of slides over time, everything in that XY, the X and Y of that plane, maintains locality. When you see, the same loop looping over and over and over as X time goes forward there, that's a loop in code. It literally looks like a loop. And then later on, when you see a jump to a different piece of code, well, that's a jump to a different function, maybe a call or a jump, different part of a basic block, or more likely a function call, another loop that runs for a while. So you can see structures in the code. It's super interesting.
So what's this stuff over here?
Yeah, we've also got the memory plane, and this is something new that we haven't shown off in some of the earlier looks at it as much. The memory view shows reads and writes to memory pages. And now it's kind of flattened because obviously the memory space is very large, but it condenses down all the memory reads and writes. And so you can see things like as the stack grows, for example, recursively calling in other functions, potentially it's going to grow, or as it's adding onto a buffer, you can see those reads and writes look like that. You can also see when you read and write from the flag page, when you're trying to steal the flag data, those are kind of highlighted down that memory page. So we get a lot of information just by looking at that. And again, it also just lets us see sort of the overall structure of this filament. So if we let this kind of play out, this is disassembling. And so on the left, up in the corner, we've actually got the disassembly box itself, right? And so we can see these instructions, and we can see even the syscalls communicate, transmit and receives are actually shown here in the communication box. And then at the end, right here, we've got a crash. I do want to point out too that this is only for dynamic analysis. We don't operate statically in just a binary. We take an input and a binary together. And in this case, we can see up in the corner the binary, or excuse me, the input was POV 408, and it's got the CGC logo. So that's a CGC POV.
Okay, that's the one that was created by the challenge author to prove
Right.
that the software is vulnerable.
It's the reference. And no, this was never used in the game. Like, none of the competitors got to see this in use. We just use it to analyze things and to see, like, does this look like they patched the thing that we think they patched, or did they maybe patch something else? Or are they vulnerable to the thing we think they're vulnerable to? And then in this case, the binary that we're running here is the reference binary. So we can see that the reference exploit works against the reference binary. It is indeed vulnerable. The green dot by the binary shows that it successfully exploits, and the red dot shows that the binary itself failed and was successfully exploited.
Here we have the side-by-side view.
Yeah, so like I said earlier, comparison is where this is most effective. So on the left, we've got a reference, right? So this is the one that you wrote. This is the POV. So the same binary is being used. In this case, it's binary 648, which is the reference binary. All the teams are running it. But the POV in the left in the gray is the reference that you wrote, and the POV in the teal is actually from Xandra. So this is their POV compared to your POV, and we can compare the two of them really easily. We can sort of look back and see similarities and differences. So in this case, I'd say that certainly one of the first similarities that I notice is the sort of the shape and the structures. You see the same pattern of loops and processing. So there might be a read until there at the beginning where they're parsing the initial bytes that come in. They're copying some buffers as we see those sort of stair-step white. And now we can also see further off in the distance some other kind of parallel structures. We can tell that Xandra's POV is a little bit longer, but it does have the exact same overall shape and structure. We see the same functions being called, and we see the data being processed in the same order, although clearly there's some sort of record kind of in this that's being parsed, because I count about 10 of these kind of white stair-step memory reads out of the Xandra POV, whereas where I only see about 6 on the reference on the left. So again, a little bit of difference, but you can tell that they're actually hitting the same parsing structure. You can see the same code being hit, and they both caused that crash. You see the red dot on each of them, so both were successful POVs.
So Xandra was made by a team called TechX. TechX is a collaboration between Grammatech and some researchers at UVA.
Yeah, I think that's an interesting collaboration. It's one of the few kind of true partnerships that we had in CGC. So it's fun seeing the commercial Grammatech coming together with UVA, the educational research, because we tend to have teams that are sort of more one or the other. You've got the pure university approaches, and then you've got the pure kind of commercial, like in Raytheon. So it's fun to see that there was a team that kind of combined these two. I also like the story about them that during the qualifying round, they were sort of the first done. Which would mean even before the event was over, they said, "Okay, we're finished. Like we've submitted all of our results," and it was only like an hour into the.
So during the qualifiers, each team was given 24 hours to puzzle over the binaries.
So, and most teams, especially if you're fuzzing, if you're doing lots and you just kind of keep fuzzing, you want to have it all, and they were like, nope, we're done. This is our results, and submitted it, and it was good enough to get it into the finals. So they were certainly right on that front. So that kind of is a good confidence.
Yeah, that's really interesting. It kind of means that maybe they have a different approach than some of the other teams.
That's kind of our suspicion, and certainly that they can have any kind of a quantifiable complete state is a really interesting statement about their capability.
Cool. Well, let's see how they do.